I'm Anil Kumar. Welcome to my series on calculus. Now, this series is going to be very interesting since students are participating globally. Now, in this second session on calculus, we are going to learn more about rate of change. In the first session, we actually learned about some basic requirements and the fundamentals which are a must to begin with calculus. So we were introduced to the concept of limit, we were introduced to the concept of tangents, and we found that tangent could be now defined as a secant approaching tangent if the 2 points are very, very close. And we came up with the formula, which is popularly known as difference quotient formula. So in today's lecture, we are going to explore more this difference quotient formula, which gives you the gradient at any point on the curve. Gradient itself is a function. So you have a function of a function. This time, that function is a gradient, which gives you the slope at each and every point on the corresponding function. Now here is Emmy from UK. She is doing GCSE level A and she is in year 12 preparing for GCSE. So the topics which we are going to cover today are something like this. Let me share my screen and then we'll go through these topics. So in Zoom session 2, which is based on gradient applications, in the first session we learned that the gradient can be given by this particular formula, which is limit h approaches 0, f of x plus h minus f of x over h. Now that helps you to find the gradient at any point on the curve. Now in this video, we will see how to estimate gradient or slope at a point. We'll also see how to calculate rate of change, interpret gradient from graph, applications of velocity, rate of change of volume, and in the next session, which will be our session 3, we'll learn about sketching graph of gradients. I hope you find it interesting. So now, Emmy is joining us from UK. Let us now begin our classes on calculus, lesson 2. Hi, Emmy, how are you doing?
Hi, sir. I'm good, thank you. How are you?
Good, good. So, Emmy, thanks for joining. And I hope you're learning about calculus as we move along. This is our
Yes.
third session, right? This is our third session on introduction to calculus. Now, in this session, we are going to learn about gradient, which some of us also call rate of change. Now, rate of change or gradient is basically to find slope at any point on the curve. Earlier, you have been doing slope on straight lines and slope on the circle. Now here, in calculus, we take up any particular curve to find, right?
Yeah.
Now, we had 2 sessions. How is your understanding about calculus?
It's better than when we started.
Yeah,
Yeah.
of course, that's good. So let me share the screen and we'll see what topics to do today. I would like you to answer some questions so that let me see if you are ready for the session and you've done your homework. Here is question number 1 for you. Estimate the rate of change at x equals to 1 for the following graphs. So we have 3 graphs here, and at the value 1, you need to find the rate of change. Can you tell
Yeah.
me what is it and how will you calculate?
So the first graph, first you plot the point. So go to x equals 1 and then go up to the graph. Yep. And I would just choose 2 points and then do change in y over change in x.
That is correct. So in this particular case, the 2 points which you could choose could be x and y intercept. For a line, for a line, any 2 points can work, right? So those
Right.
are good points, and in this case, you can read them, which are 6 and 3, and that gives you a gradient. Will the gradient be negative or positive?
Negative.
Perfect, because the line is coming down. How
Yep.
will you do for the second graph, which looks like a cubic function?
So at x equals 1, there's a straight line. So that tells us that the gradient is 0.
That's perfectly fine. How about the third one?
So there is no gradient for this one, because on the left-hand side, the gradient is less than 0, and
Yes.
on the right-hand side, the gradient is more than 0. So
Yes.
it's not at the point at the corner, there is no gradient.
That is perfectly fine. Beautiful answer. So at any cusp or a corner, the gradient value cannot be found. Since when you approach from the left side and right side, you do not approach the same value. And that is the concept of limits, right? So let's take the second question here, which is the graph of f of x is equals to 4 minus x squared. And that is given to you right there. Now, I think you can see the graph, right? That is the graph for you, correct?
Yeah.
You need to answer this particular question. So can you read the question and answer for me?
The graph of f of x equals 4 minus x squared is given below. Which of the following statement is always true for the gradient of f of x? So A, gradient is always increasing. B, gradient is always decreasing. C, gradient is decreasing, then increasing. D, gradient is increasing, then decreasing. E, none of the above is always true.
Okay, so what do you think is the right answer and why?
So I think the answer is D.
D?
No, sorry. I think the answer is B.
B. Okay.
B, because
B. Gradient is always decreasing. How do you say that?
So if you draw a tangent at, let's say, this is how I do it. I don't know if this is the right method.
Okay.
But at -2, if we just quickly draw a tangent, so we can see that the gradient there is positive.
Yeah.
And then as you get to the turning point, which is 4, at 4, 0, 4, it's a horizontal line, so the gradient is 0.
Correct.
And then if we draw a tangent at 2, 0,
yes,
we can see that the gradient is negative.
Yes.
So it is quite a trick question, because initially for me as well in the beginning, I thought it was increasing then decreasing, which was D. But actually, if you look at the overall graph, it goes from positive to negative. Therefore, overall, the gradient is always decreasing.
Always decreasing. Perfect. That's a brilliant answer. Here is question number 3 for you.
This one.
Yes.
Right. Oh, okay. So I just start by. Okay, so I start with the general.
Can you read the question, please, for me?
All right, yeah. Can I just move that? Determine the slope of the tangent line at the point P 1, -3 on the circle given by the equation x squared minus 4x plus y squared minus 8y plus 16 equals 46.
Yeah. How will you do this?
So there's a general form equation for a circle, which I saw in one of your videos, and I got that as, so you said x minus h whole squared plus y minus k whole squared equals r squared, where h and k coordinates are the center of the circle and r is the radius.
Perfect. That is a transformed circle. So instead of circle being at origin, where the equation is x squared plus y squared equals to r squared, if you translate it right by h units and up by k units, then the equation becomes x minus h whole square plus y minus k whole square, right? Simple translation, okay? And then those are the center points. Now, with those center points, what will you do and how will you find those points?
So I initially first start by doing x squared minus 4x plus y squared minus 8y, then move the 16 to the right hand side, so equals 30.
Okay.
And then so you figure out the center of the circle by taking the two, so minus 4x and minus 8y, and divide them by 2, and then just like do the inverse of it.
Yeah.
to get the center of the circle.
Yes, that is right. That is right. And we also say completing the squares method. So you kind of complete the squares and you get x minus 2 in this case whole square, right? And y minus
Yeah.
1 whole square. Perfectly fine. That's brilliant. So you get your center. Then what?
So center point is 2, 4 then.
Yep.
And then so once you get the center, then what happens? Well, I drew a diagram.
Okay. So I
That
think
kind of
you did the right thing.
visually.
Here is a short solution to the same thing without the diagram, of course. So
Right.
what it did was correct. And you found the center point to be 2, 4, right? And
Yeah.
then you have the point given to us as 1 minus 3. Using these 2 points, we can find the slope of the radius, which is 7. And tangent is perpendicular to the radius, and therefore negative reciprocal is the slope of the tangent line. So here you use the old
Well,
principles and you got your result. Now, that you cannot do for any graph, any other curve, you can definitely do for circle, correct? So here we have the fourth question, which is now based on rational functions. So now we have to apply the techniques learned in our introduction to calculus. Now, can you tell me, in question number 4, it is consider the rational function f of x equals to x square minus 1 divided by x square minus x. Write the number of points on the graph of f of x that will have gradient of 1, 0, undefined, or minus 1. How will you do this question?
so I sketched the rational function because obviously I like to see things visually, otherwise I can't. So I expanded the brackets, so I got x plus, so on the numerator you get x plus 1, x minus 1, denominator x, and then x minus 1.
Yes.
So I'm actually kind of explaining how to sketch the graph. It'll be really quick. So then you cancel the 2 like common terms, which is x minus 1, x minus 1. So then you get a whole, and then there's so many other stuff. So then when you draw the graph after everything, and you get the horizontal asymptote at y equals 1, you get 2 decreasing, so it's like a reciprocal graph where they're both decreasing. Oh yeah, there.
That's it.
So you
this
can
is what
cancel,
you're explaining.
Yeah. So you can cancel the gradient, which is, it says number of points that have a gradient of positive, because both are negative, so that's out. And then it won't be 0 because both of them are approaching 0, but they're not actually 0.
Yes.
So that's also out. It's between undefined and minus 1. So, I mean, you drew 2 lines that are negative. However, those points aren't the turning points. So is it undefined?
So on the vertical asymptote, we have undefined gradient because that point is not actually in the domain. So this is undefined. So, right?
Right.
Now, that is not actually in the domain, but yes, when you say write the number of points on the graph of f of x, that will have a gradient of undefined. There is actually no point at all since this part is not on the graph of f of x. You get the idea, right? So, strictly speaking, this should be 0. This should not be 1. This should be 0, right? Because this point is not in the domain. So, in this particular graph, there is no point where the gradient is undefined. Now, it does not have, as you explained, a positive gradient. So, for 1, we have the answer which is 0. That is correct. It is never 0. So that is also 0 because it is approaching 0, but it, that is at infinity, it is approaching, but it is never 0. The last part, it is minus 1. From the graph, someone may conclude that there are 2 points. However, the other point is a whole. So we cannot consider that particular point. So there is only 1 point here where the gradient is minus 1. You see that?
Yeah, okay.
Example, and many times we do a mistake of ultimately including the whole in our answer. You cannot. Nor
So there's no
the vertical asymptote. Yes, Sammy.
So there is no gradient at 0 at the whole, sorry.
No, no. So at discontinuities, you cannot have gradient because that point is not in the domain.
Oh,
So the
okay.
answers for first three are 0, 0, 0. And for the last one, there is one point where we have a gradient of -1, as can be seen by this purple line. Perfect?
Mm-hmm.
The green dotted line, you may get confused, however, that goes through the hole, and therefore it cannot be considered as a point on the graph, right?
Right.
Make a note of this particular question. It is a very tricky question and is sometimes asked in the examination. Now we have an application question here. Rate of change whenever we talk about it is like, like population of insects, population of animals, or the virus. Many problems are solved with rate of change, and there are many functions which depend on the variation of one factor or the other. Now here is very good example for you. So Amy, can you read the example and explain the solution?
Yeah, sure. So the temperature T in degrees Celsius varies with the distance d in kilometers above the Earth's surface according to the equation T of d equals 60 over d plus 2. Determine the average rate of change in temperature with respect to distance between 3 kilometers and 8, instantaneous rate of change in the temperature with respect to distance at 3 kilometers.
Perfect. How will you answer this question?
So with the average rate of change, I just did T of 8 minus T of 3 divided by 8 minus 3.
Perfect.
And I got minus 6 over 5, which is
Okay.
minus 1.2.
Okay.
And then with B, I just used that. Oh, or you can use the difference quotient formula.
Perfect. Perfect.
So T3 plus H minus T of 3 over H.
Yes. So
And yeah,
it's difficult to explain. So here is the solution. Did you do something like this, right?
yeah.
Perfect. So you apply the difference quotient formula. It's direct application. But the key point here, which I've seen many students making mistake, is right at this point. The function is d plus 2. Remember that. So when you write t d plus delta d, don't forget this 2 here, right? Don't
Oh,
forget this 2.
okay.
That is a very critical part, and at times in solutions, I've seen students just missing this 2 and getting a wrong answer. Otherwise, great application of the quotient rule, right? So that's how
Right.
we're
Yeah.
going to do it. Perfect. Next question is based on semicircle. Find the gradient function of the curve f of x equals to square root of 25 minus x squared. So whenever it is kind of this function, you should recall that it is equation of a circle where you isolated y and you're only looking into one half of it, which is the positive half. So it is a semicircle, right? You
Oh,
need
okay.
to find the point on this curve where the gradient is minus 4 over 3. So this is a very important equation. Sometimes we get confused, but it is basically a semicircle. So Amy, could you solve this particular question?
Yeah. So with question 6a, I just used the difference quotient formula, and I got minus a over square root 25 minus x squared.
Okay, that is correct. So you substitute a here, which is a good thing for x. You get your formula. That is correct.
Yeah.
And then we are given the gradient is minus 4 over 3. So you find the value of a, right?
Yeah.
Perfect.
Oh, I actually just did it by drawing. I don't know if you can
Oh,
do it like that.
okay.
And then I just went up like, I know it has to be negative, so I just went minus 4, and I was like, oh, it goes 4 across, up 3.
Good.
So,
So, Amy, I'd like you to make a note of this so that you understand this is also a way of doing it. Uh,
okay.
Graphically, also, you could do it because it is again a circle, right? Semicircle.
Right.
You could definitely do. And graphically, if you do this question, you will do it in 1/10 of the time also. This is a brilliant approach which you have adopted. When you do algebraically as shown here, here is a very tricky step. Now, the step here is we have minus 4 over 3 equals to the gradient itself, because we are given that the gradient is minus 4 over 3, correct?
Yeah.
And you get an expression which is x over square root of 25 minus x squared. Now, when you equate them and solve at this particular stage, you know square root is always positive, right? And
Right.
so the value of x has to be positive. So the note which I have written here in red, that 3x has to be positive. It's very important. Since at the end, when you try to solve this equation, you get 400 equals to 25x squared. And when you square root, we are not taking the negative term. We are only taking the positive term, not the negative term. And if you, from your drawing also, it is very clear that you cannot take the negative term. That's a tangent has a positive slope, right? Only on the right side, quadrant 1, it has a negative slope. And that gives you the coordinate of the point. Perfect. So that is how.
Right.
Good. Now, question number 7 here is a pebble is dropped from a cliff 180 meters. After t seconds, it has fallen a distance of s meters, where s of t is 5t squared. Find domain of s, find average velocity of the pebble in the second second, t. Show that the average velocity of the pebble during the time interval t equals to 1 to t equals to 1 plus h is 10 plus ht. And d is find instantaneous velocity of pebble at t equals to 1. Specify your answer. So, Amy, how will you approach to solve this particular question?
So with A, I just did s of t, so equals 5t squared. I substituted s of t for 180, and then you just solve it algebraically. So 180 divided by 5, 36, t squared equals 36, so t is 6.
Perfect.
With B, find the average velocity. So like we did before, I did S, so because it's saying in the second,
Yeah.
That's the between 1 and 2.
How do you know that? Second is between
Because
1 and 2.
the first second is 0 and 1, because...
Yeah. That's a very tricky part. It's very confusing. Second.
Yeah.
So the first second is from 0 to 1. Second is from 1 to 2. Yeah.
Yeah, it's about the wording.
Yeah.
Right. And then you do S of 2 minus S of 1 divided by 2 minus 1.
That's right.
And I got 15 meters per second.
Okay.
Up there. And then with D, it says find the instantaneous velocity. So I just used the average velocity one, but you can still also just go through the process again, like you've done, and use the difference quotient formula. But I just subbed in. So when you use that formula, 5h plus 10, and you substitute h as 0, you get 10 meters per second.
That is true, because this was a part of the question in C, so you have to derive this formula. Once you derive this, then in E, you could just substitute the value of h as 0 and find your answer.
All right. Yeah.
Fine. Yes. So we are almost at the end now. Here is the last question for you. How will you do this rate of change of volume question? Can you read the question?
A spherical balloon is inflated. Show that the rate of change of volume with respect to the radius is related with the surface area of the balloon at that instance. Find the rate of change of balloon when the radius is 10.
Yeah.
Okay, so I went a bit off and then I came back again, but I think so. You can use the difference quotient formula. But I think first, before we start anything, write the volume of a sphere.
Yes.
So 4/3 pi r cubed.
That is correct. So normally the formula is given to you in the test papers. If you don't remember, it is already provided. It will be. So, okay, that's correct. 4/3 pi r cube is the correct formula. Yes.
And then I just did, so 4 pi by 3, and then r plus h cubed. Then you expand it using Pascal's triangle. And see, here's when I went wrong. So I started to expand the 4 by 3 and then like do every bracket when you can just cancel out.
Yes.
I know. So I stopped there and I was like, oh, okay, we need to cancel those two out. So it becomes much simpler. And we get to the solution as 4 pi r squared, which is the surface area of a sphere.
That is correct. Now, Emmy, my suggestion is that for this, for cube, you should always remember the formula. Just as for square, you remember, right? A plus b whole square is a square plus 2ab plus b square. Similarly, a plus b whole cube is a cube plus 3a square b plus 3ab square plus b cube. It's good to remember these two formulas, and for higher orders, you should use Pascal's triangle, right? So, and then you can definitely write down the answer. Now, coming back to the units of this question, what are going to be the units of this question? The unit rate of change of volume. Can you explain me the unit?
Right, so the centimeter cubes is pretty straightforward. It's the volume.
Yes.
But per centimeter, because the question says find the rate of change of volume with respect to the radius.
Perfect. So
That
radius
part
is
is
in the
centimeter.
denominator, and therefore that centimeter comes for the radius. And you should not be canceling it and should not be writing as centimeter square in the test question. Is that clear to you, right?
Yeah.
Correct. So that's fantastic. I think you have understood the chapter. The whole idea of sharing these questions with you, and you made a great attempt to solve them, was to understand whether you really got the gist of it or not. So you're absolutely ready for our next chapter, which will be on limits. We are going to start that chapter tomorrow. Now, here is the set of questions which we answered just now. I hope all our viewers must have liked these set of questions. They are representative of your introduction to calculus. If you can actually solve these questions, you're absolutely ready for the next chapter or unit on limits. So, Amy, how do you feel?
I actually feel quite good. So much better than when I started. Like everything's making sense now. And it's actually like it's just getting over that little hurdle at the beginning. But now, yeah, it's really good.
Really, I'm so happy about it. And Amy, I think now you're absolutely ready to solve most of the questions in your book. So make an attempt to solve them all, right? What I also noticed is that your GCSE level A course, that they have introduced the derivatives quite early on. So you attempted to use the power rule to find the derivative
Yeah.
instead of the difference quotient method. Perfect. I will actually suggest you not to use the power rule for now. After about 2 or 3 lectures, we will be doing the derivative, and then you
Okay.
revisit those questions with the power rule. For the time being, practice the difference quotient method.
Okay.
But it is a very important concept and will definitely help you moving forward. It does not only help you in calculus, I mean, you've done polynomials, you've done rational functions, trigonometric functions, exponential functions, and logarithmic functions. In all these functions, when you do rate of change, you always use difference quotient method. So it helps you in so many other areas. It's a good time to practice. And later on, we'll use standard formulas and quickly find the derivative. I
Yeah.
hope you enjoyed this journey and was a pleasure to make this video with you and have you as a student. Thanks a
Right
lot.
back, sir. Thank you, sir.
My pleasure. Have a great day.
Yeah, you too.
Bye. Thank you.